the survey at the end of this webinar. So now it is 1 o'clock Geneva time. So I would like to open this webinar. Warm welcome to all the attendees, and thank you very much to all the panelists. This is a part of the online, the COP6 online event, which is about effectiveness evaluation draft report of the open-ended scientific group. We have invited the team leads of the open-ended scientific group for the effectiveness evaluation of the Minamata Convention to present the work so far. Sharifu, can you switch to the PowerPoint presentation? Sharifu, Yes. Okay. So my name is Isak Toda, Senior Program Management Officer of the Minamata Convention Secretariat, and welcome to all to this Minamata Convention Pre-COP6 online event on effectiveness evaluation, open-ended scientific group. So next slide. I'd like to introduce the speakers in the order of speaking. The next speaker will be Dominic Bali, the co-chair of the OESG, and then Sandy Stephen, OESG co-chair, and also the air monitoring team lead from Canada. Karina from Argentina, and Olga from Australia will present on biota work. And Yanya from Slovenia leads the human biomonitoring team. Adrian from Switzerland and Svetla from Bulgaria leads the other medias group. Ronnie from Sierra Leone, Lin Will from South Africa leads the emission releases team. Noriyuki from Japan leads the integrated analysis team, and Ben from China leads the future vision team. The next slide, please. So just a bit of introduction. The effectiveness evaluation is being done under the Article 22 of the Minamata Convention, in which the convention says that the conference of the parties will evaluate the effectiveness of the convention, and the evaluation will be based on a number of pieces of information, of which the monitoring information is one. The COP4 in 2022 agreed to begin the first effectiveness evaluation and establish the open-ended scientific group. COP5 in 2023, we agreed to consider the outcome of the first effectiveness evaluation at COP7, which is 2 years ahead. So the next COP6 is just the follow-up on progress and the conclusions of the effectiveness evaluation. First effectiveness evaluation will be done at COP7. And COP5 established the effectiveness evaluation group and adopted 36 indicators for effectiveness evaluation. The first one is the level of mercury in the environment and humans, which will come from the work of OESG. The next slide, please. So we have COP document 6/16, which is a very brief progress report on the effectiveness evaluation, and it includes the overview of the work done by, firstly, the effectiveness evaluation group, which is established after COP5, co-chaired by Lin Loy, of Antigua, Barbuda, and Itsuki from Japan. But note that Itsuki Kuroda resigned in August this year, and the group is expected to elect a new co-chair, hopefully next week when they meet online. And Open Scientific Group is co-chaired by Dominic Barry and Sandy Stephen, as I introduced, and met once face-to-face in Minamata. I see once because this is the progress after COP5. The OESG actually met twice. And yes, and there are information documents. The first one is preliminary draft outline of the first effectiveness evaluation report, and information info document 23 is still to come, but we are now developing an update on the work of the OESG. The next slide, please. So the OESG, this is a photo from the meeting in Minamata in March this year, and we have 42 members, one from nominated by parties, each party, and the work is supported by experts in roster. These experts have been nominated by parties or other stakeholders, and we have 112 in the list. So we are a big scientific team, and next one is my last slide, I think. Next slide, please. So this is an overview of the schedule from now on for the effectiveness evaluation, and as presented later, the OESG has circulated an overview of available monitoring data in June for party review, and we expect to circulate the scientific report very soon for party review. And then the effectiveness evaluation group will take over by meeting in hopefully in January and October next year. And the COP7 is expected to conclude on the effectiveness evaluation. So I think this is my last slide, and I would then invite Dominic to speak as OESG co-chair.
Thank you so much, Isako, for that introduction and also for setting the scene for this meeting. And coming back to the presentation, and I'm just going to present what is the main role of the OSG, the Open Index Science Group, and what we are doing and how things are being done under our team. So especially, what does the effectiveness evaluation and scientific report addresses? Because one of our key role is to develop the scientific report that will see for the effectiveness evaluation recommendation. Especially that will be the entry document for the EEG group. So if you remember well, at COP3, the decision MC COP3/14 agreed to have 4 policy questions to address the effectiveness evaluation. And one of these key questions, especially question number 3, was related to, is the one which is directing our work, especially. Just to know that if those changes resulted in changes in levels of mercury in the environment, biota, and vulnerable human populations, that can be attributed to the Minamata Convention. So answering that kind of question request a series of scientific analysis based on data collection. So based on that, also the OSG group is also interested to learn from the lessons available for the future evaluation, effectiveness evaluation. So based on that, we agreed to know about. We are trying to identify the gaps in the knowledge and different capabilities that are barriers to answering the policy questions above. But also, based on the recommendation that we make, we also intend to define the different actions that could be taken to address these gaps or barriers. Next slide, please. So on the data analysis questions, the data analysis questions are trying to answer to identify the current levels, the temporal trend, and the spatial patterns. And based on these different points, we The OESG seeks to answer to identify the current levels of mercury emissions and releases, for example, and the levels of mercury observed in air, in biota, in humans, and other media in sites, especially from the remote anthropogenic sources and even the one affected by local anthropogenic sources. With regard to the temporal trends, the OSG to, to identify or to quantify the levels of mercury and mercury emissions and release, especially are observed in air, and how the different changes compared to the timeline of the Minamata Convention since the negotiation of the convention, its entry into force, and even now its implementation. And we intend also to identify the specific mitigation measures, especially that have contributed to the change in emissions and releases, and also how the mercury levels emission and releases and mercury observed in air biota are expected to change in the future. With regard to spatial patterns, we are trying to see how the current levels and temporal trend vary geographically at global scales. Yeah. Next slide, please. Other points that are covered by the data analysis questions also are related to the source and process attribution, the exposure and adverse effect, and the process understanding. So with regard to the source and process attribution, we intend to respond to the different questions on the fractional contribution of contemporary anthropogenic emissions and releases to current mercury levels observed in air, biota, humans, and other media, especially. We also work on providing information on how these contributions levels have changed over the timeline of the Minamata Convention, and even how these contributions level and their trend vary also geographically at global scale. With regard to exposure and adverse impact, the OSG also works in identifying how the current levels also are observed, and even the threshold that could affect the humans and other living organisms. And also we are also working on the process understanding. Next slide, please. Okay. With regard to data collection and analysis processes, the OSG we launched a call for data to different parties. We received the different data providers expression of interest and to submit data, and based on the different data, especially in emissions and release, in other matrices, in biota and human monitoring, all these data have been collected and stored in the cloud, which serve for the different teams for analysis. So statistical analysis have been made. Multimedia global modeling is also performed, and multimedia limited case study are being developed also to try to understand the current status, especially in the case where there was no available data for a long time series. Based on that, the data availability report have been developed, and right now the teams are developing the data analysis report, which covers the different media specific analysis, the available observation, the current levels, the spatial patterns, the temporal trend, and even the exposure adverse impact. Additionally, we also have the integrated multimedia analysis, the source of process attribution, and the process understanding. All this information will be gathered in the scientific report to support. Next slide, please. And I think that will be my last one. What are the different products that have been generated by the OSG since it has been created? On the different plans that have been developed, we had the emissions and releases plan, data collection, which was developed, the observational data collection plans and data analysis plan. All these documents have been presented at COP5 in 2024. And right now we have also, based on the data that have been collected, the summary of available data, especially on emission, release, and observation, has also been produced. It has been sent to share with all the parties and the different participants to the COP, especially through the informative document in this year since June. And right now we are working on the data analysis document and the gaps in the recommendation. All this information, all these documents are due for December 2025. where we expect to send them to, we expect to have them with the reviewed by the parties after the COP. So we will be working, we work on that now, just by the end of this month. If they are ready, we can share them with the parties, and later by December, we expect to have them reviewed by the different parties. And based on that, also, we will provide a scientific report based on the available data and analysis for which is expected for June 2026, and also the lesson learned and gaps and recommendation reports also to be, which is also due for June 2026. Thank you so much. And Sandy, I hand over to you. Yeah. Thank you so much.
Thank you so much, Dom and Asaku. Good morning, good evening, good afternoon, everyone. Some may be wondering why it is that I am sitting in this co-chair seat right now. We want to thank very much to Dr. Terry Keating from the US, who was our co-chair up until September or July. We want to thank Terry so much for his leadership and for all the hard work he's done on this program. But Terry had to step down from the role, and so I was asked to step in. So it's some pretty big shoes to fill, and I hope that I can at least come up halfway to the work that Terry's been able to do through his leadership. So just want to thank Terry and acknowledge why I'm sitting in the co-chair position. But I'm not only sitting in the co-chair position, I'm also still leading the air group, or the atmospheric group. So I just want to go through a couple of slides here on where we are right now in terms of the air product for this first draft. And I emphasize draft here for the scientific report. So let me just go through where we're at right now. So next slide, please. So one of the questions we have is where is the data? What kind of data we have? And we did present in the product of data information earlier this summer, but we have been getting data coming in all the way until the end of August. So this is much more updated. For air, we're doing 3 different types of air measurements we're looking at. One is called active air, total gaseous mercury. We're doing passive air, which is gaseous elemental mercury. And then we're looking at the wet deposition of mercury. So you can see here, it looks pretty thorough around the world, some large gaps in some areas, but this is just all the measurements currently from 2010 forward. So it does give us a bit of a skewed view of what's going on, but that is where the data we have been that has been submitted comes from. So next slide, please. So the questions that we're looking at for the air, of course, match with what Dom has said. And so I just want to mention that this is actually the first time that we've done a global approach to the atmospheric data, in the sense that we've collected all the data that was submitted and put it together in one data set and are analyzing it as one data set. In the past, it had been each region or group would analyze the data and present that. This is the first time we've done it all ensemble like this. So we're looking at the temporal, spatial variation, the trends. We're looking at some statistics, a regional analysis, and then this work will feed through to the model validation and the modeling work. Next slide, please. So to give you a snapshot here of the preliminary levels of mercury in the air, you can see here that the so we have different, when you pull things apart, you can see in our active monitoring, the passive monitoring, we have for TGM, total gaseous mercury, and gaseous elemental mercury, we have different sites. So it's very difficult to say that they look the same because the sites are different. But you can see through this that the more red the dot is, the higher the level of mercury in the air is. The bottom plot will show you where the atmospheric mercury deposition, and this is wet deposition, so through rain, in some of the different regions where we have data. We only have data from these 4 regions for the wet deposition. And you can see that the different areas have different levels of deposition over time. Next slide, please. So we've done a preliminary trend analysis, and in these, we've done it for the active sites for total gaseous mercury and the wet deposition. And that is because there's enough data over time to be able to establish statistically significant trends. So for the passive monitoring, we're just not there yet to be able to do this. So I just want to point out here, this is data that all the data that has been submitted over the years, not just from 2010 forward. We haven't done that yet. So green means the concentration levels are going down over time. White means there is no trend visible, and red means there's an increasing trend available. And this is just a snapshot because this is data over the entire time period. We do know that the trends of mercury are going to change over time depending on what's going on in the environment and with emission levels. So again, just snapshots here. Next slide, please. Just to show you here, we're doing some very basic statistics for the active, passive, and wet deposition for all the sites across that have of data that have been submitted. So again, it's the total data set all lumped into one number. So I just want everyone to know that this is taking an enormous amount of data and piling it down into one number. But we're just giving this to you as a draft to see what we can do. Next slide, please. I want to show that we are doing some regional analysis, and this is some frequency distribution of the levels of mercury in each of the regions. The blue bars are the frequency distribution of the mercury concentrations. The red level just shows you the same 1.5 concentration, just to show you a bar and to show that each region that we have data is actually shifted slightly differently. Next slide, please. So the thoughts so far are that this air is probably, of all the media, the easiest, but it is not easy by any means. So I just wanted to sort of put that out there, that this was probably the easiest data set to deal with, and it is very complex. Just to get it into the database has taken about 10 months of back and forth and figuring this out. This is a huge undertaking that I think I underestimated. So far the lessons learned is there is a bit of a disconnect between what the COP is asking of us and what we were able to produce with the structure and the tools that we have so far. We do need more engagement from parties on data delivery. That was a big challenge. The time frames over which the data is collected need to actually be similar in a similar time, and we really do need some kind of a global monitoring program to constrain everything so that it's it can provide us the data set that will give the answers to what the COP needs. We definitely need one common spot to put the data in. So having this database right now, it's just within Environment Canada. We've pulled it in. I have expert data people that are doing this work. So it's that we will need. And the politics are tricky to navigate with the science. So that's one thing. And we need to set expectations of what is possible early on. So that's just a quick summary of what we're doing with the air so far. So I will hand the microphone back over.
Your microphone is muted.
Sorry. So thank you, Sandy. And since we are running a bit late, I think I will need to ask the speakers to speak in a bit less than 5 minutes. So maximum 5 minutes. So I now invite Karina to speak about the biota work. So Karina, please.
Okay. Good morning. Thank you, Dom, Sandy, and Isaku. Good morning, good afternoon, good evening, everybody. I'm happy to be here to share the progress on the scientific report about Biota Group. This is the report that was working also colleague with Olga, but I sent also to the all Biota Group to the hard work, mainly during the last 3 months. Next slide, please. Okay, an initial question to consider is what data has been received and analyzed for the biota group? Well, the map shows the sampling locations of submitted data, including both individual mercury levels and aggregate data such as mean values. Subset of the submitted data that met the minimum data requirement were used in the analysis. Next, please. The OESG has received 56 submissions on total and methyl mercury concentration across a range of taxa, including invertebrate, fish, amphibians, reptiles, birds, mammals, and plants. But particularly, data on mercury concentration in amphibian, reptilians, and plants remains limited. So for the purpose of the first cycle of effective evaluation, the data analysis had considered total mercury in invertebrates, fish, birds, and marine mammals. It is important to note that 73% of the total data collected correspond to fish and 17% to birds, while invertebrates and mammals account for around 5%. Who were the contributors of this data? For one side, you have several multinational monitoring programs, including AMAP, OSPAR, and HELCOM, related with the Arctic monitoring, with the Northeast Atlantic area, and also with the Baltic Sea. Moreover, national and subnational organizations from Canada, United States, Norway, France, Finland, and other countries, and the Biodiversity Research Institute, who provide data from a database of about 1,348 published articles, covering a diverse range of taxa and tissue types. Next up, please. Well, what are the key messages regarding the current mercury levels in biota? Firstly, current levels were defined as total mercury concentration measured between 2014 and 2024. But it is evident that the most intensive sampling and mercury monitoring have been done in North America, Europe, and East Asia, with significant data gaps for most other regions of the world. Therefore, enhancing monitoring is highly required in underrepresented regions, particularly Africa and Latin America and the Caribbean. But it is also important that the monitoring should be also focused on underrepresented taxa, such as invertebrates, blood from birds, and marine mammals. Next slide, please. The most frequently sampled matrices were muscle of fish, followed by feather and eggs from birds, soft tissues of invertebrates, and liver and muscle of marine mammals. Next one, please. In the table, you can observe that across region and species, the mercury concentration varies widely, often spanning several orders of magnitude. Next one, please. Mercury concentration were significantly elevated at sites with known sources, such as artisanal small-scale gold mining and metal smelting, comparing to control sites. Next one, please. The case of the biota, invertebrate, fish, bird, marine data are not suitable for global scale spatial pattern analysis. It is due because to the limited geographic coverage and broad variability on the species and their trophic positions among the different regions. Therefore, regional, spatial, and also local comparisons were performed. The next one, please. Following with the key question, another one is how the current level of mercury observed in biota compared to established national and international benchmark level associated with adverse effects. But at this point, the analysis data have identified that some species show mercury levels indicating a high risk of toxicity. For example, particularly the levels in the liver of some marine mammals or certain fish species, whether shark or some originated from Europe, the Mediterranean Sea of the Arctic. Moreover, there are 10% of the bird feather data showed values corresponding to medium, high, and severe risk of toxicity. In the figure, you can observe an example of mercury levels in fish muscle, expressed as weight versus toxicity reference values. Horizontal color lines indicate toxicity reference values in purple color of toxicity. Next one, please. Next one, please. Okay, yes. The another question is related to how do total mercury in species vary geographically over time. I mean the temporal trend. That is an important point, but you have some trouble with that because due to the lack of data, only limited temporal trend analysis could be conducted for certain taxes, based on case study conducted at local and regional levels. Thank you.
Thank you. Thank you, Karina. I think you highlighted the importance of case studies, which I think Noriki will speak to a bit later. With that, I think I will invite Yanya to speak to the human biomonitoring.
Hello, I will just quickly jump into the overview of our work to save the time. So starting with what data we have, this is the figure that presents the number of mostly cross-sectional studies and also bird cohorts by country. So the more intensive is the color, the more studies there is. So as you see, some areas are of course largely underrepresented, but in terms of population groups that we are tackling with our research question, we have a quite good coverage. I have to emphasize here that most of the data that we are now able to work with was obtained through the literature search. Only part of it was obtained through the OESG repository. So overall, we have collected data from 280 studies and for 50 bird cohorts. And of course, these are then further stratified by different population groups, stratified by region, by age, by year, and so on. And so we have more than almost 600 different age groups with the measurement in which have at least one biomarker measured for mercury exposure. What I'd like to stress here is that we have a really good rich data for indigenous populations. In latest assessment in 2018, and also quite rich data for ASGM communities. Next, please. Next. So this is actually
I think we lost Yania.
Yeah, it seems like that. So Sharifa, can you click several times because there should
Sure.
be.
Yeah.
So I think since Yanya, is your sound back? Doesn't seem like that. So in order not to lose time, I think I will move to other matrices. And when Yanya is back, we go back to that. So Adrian Svetra, I'm not sure which of you are presenting which part, but I leave it to you.
I'm starting. Thank you, Tsako, for the introduction. In the next few slides, my colleague Adrian Mestrod and I will present summary of the results for the multiple matrices which were not covered by the previous speakers, mainly water, soil, and environmental archives. And I just wanted to thank all the team members who contributed to this. So next slide, please. With the ocean data analysis, it was done by compiling data from scientific publications because there is no systematic monitoring of marine mercury concentrations. But luckily, we had an increased number of research data cruises and that have been done, and the data was published. So the data sets contain both total mercury and methylmercury data, and the analyses are based on 20 years of data between 2005 and 2024. And what you see on the figure here are the total mercury concentrations on the top right panel, which are marked with different colors. The darker the color, the higher the concentration. And then the bottom one is the methylmercury concentrations in globally. And so they are also done by the IPCC regions. Next slide, please. Overall, our conclusion is that we were able to do the analysis, and the scientific publications covered about 62% for total mercury and 42% of methylmercury for the open ocean and coastal regions. The highest concentrations were found in surface ocean and closer to the polar regions, and the lowest were in the South Pacific Ocean. The ratio between total mercury and methylmercury is usually highest in the mid-latitudes and equatorial regions, and no difference was seen in the polar regions, which was different from the observations for total and methylmercury. Again, the southern hemisphere overall had lowest percent of methylmercury compared to the northern hemisphere. And the only correlation that we were able to discern from this data is correlation with salinity for total mercury in the polar regions, while for the methylmercury we did not find any correlations, and no correlation was found in the coastal regions. Overall, our conclusion is that even though we had good data from the research data cruises, we need a better coverage because some regions and coastal regions are not covered at all. Method development and more laboratory and method intercomparison studies are needed. And we propose that the utilization of passive samplers is going to increase the availability of data that can be put in official database, extending the current one. Next slide, please. So these the three slides that follow will be about freshwater mercury, and the terrestrial freshwater monitoring networks still remain underdeveloped both regionally and globally. And what we obtained here are we had only 7 submissions for surface water measurements in rivers and lakes. And as you see on the figure on the right, it's very patchy and doesn't have a good global and spatial coverage. Most of the data are site-specific and local. They're not part of any monitoring activities, which is an issue because we were not able to discern much trends. These data sets are also very limited in time where they were done. So the significant data gaps persisted and are as obviously not only in developing countries, but also prevalent in developed countries. Next slide, please. The inadequate spatial coverage made it difficult us to assess any regional or global patterns. The problems we encountered is with the data usability as a whole, because the detection limits used by different studies that we looked at were different, and then some of the data was very old from the 1990s, and the detection limits for these old data are much different than the contemporary ones that we're using, so made some of the data unavailable for any analysis. What we did is we conducted some scientific literature review, but as I mentioned, the data is not long enough, and it's based on local studies. Multi-decadal scientific monitoring studies simply do not exist, and that is a big issue even moving forward for the assessment of the Minamata Convention effectiveness. There was no way to differentiate between point and non-point sources because some of the data just don't provide this information. Based on the literature review, what we concluded is that in general, the rivers seem to have quite variability in mercury concentration that is driven by flow and particle transport, and it's closely linked to the mobility of dissolved organic carbon. In lakes, mercury is mostly influenced by sediment interactions, change in redox conditions by season, and then the lake water oscillations. DOC, in this case, the dissolved organic carbon, plays more stabilizing role. What we also did is we looked at case studies with long-term data for a few areas. One is rivers in Sweden, where we found decreasing trends between 2000 and 2015 in some of the rivers, but then this trend shifted to increasing, and so this highlights that we have some shifting patterns between different timeframes. Also, we looked at 3 different lake ecosystems in the United States that were away from point sources. They also had a different message. We found that global and regional sources still control mercury concentrations in some of the lakes. Others appear to have responded to decreases in atmospheric depositions, but fish population did not respond due to some changes with other parameters that control metamercury production. Next slide, please.
Svetlana, can you speak to the key points?
Yes, here they are. And so, as I mentioned, the convention mainly relies on existing data, and the main issue with us, with freshwater, is that we don't have existing monitoring networks, and that presented an issue with us to discern any patterns, and we need to include this in the future effectiveness evaluation. That's it. Moving to Adrian with the rest of the matrices.
Adrian, you're mute.
I thought I was unmuted. Thank you, Isako. We received data for total mercury only, and the data we received was good for USA and Australia, but from other countries was medium to poor coverage. And for most of the world, we basically have no data, and there's no methyl mercury data either. Next. So the data covers different time period, as indicated here on the graph. But there's also no repeat sampling, so it's difficult to do temporal trends. Our key findings, or the first part of our key findings and limitation, is that the spatial variability of total mercury in soil is quite large, and this is due to various land use, land cover, the effect of geogenic mercury and anthropogenic activity, but without having this information in the database, it's very difficult to disentangle it. Next. We found that the levels in soil seems to be regulated by the presence of soil organic matter and or pathogenic oxides, but this relationship observes they can strongly vary depending on the intensity of the mercury input. We do need monitoring program for Africa, Asia, and South America because there's not much data available. And we need consistent sampling, extraction, and analysis needed. So if you sample the soil at 10 centimeter or 20 centimeter, or if you do the extraction with acid, or if you do a total analysis with the direct mercury analyzer, the results will vary slightly. So we need to be able to homogenize this to be able to compare the data. We also need monometal mercury and ancillary parameters such as soil organic matter, but that would be nice to have only from selected sites, as we realize it would be difficult to have for everyone. Next. So for the environmental archive there, we were able to get quite a lot of data. There was quite a huge amount of work being done. However, the data set is still heavily weighted toward North America, with most of the cores originating from this area. And there's much less data also for other regions of the world and also for recent time periods. So we need basically new lake sediment core collection, especially if the lakes have already been analyzed. That would be great and would enable more robust temporal assessment. Next. Overall, the key finding was that the mercury concentration and fluxes, they are low and comparable between unimpacted and impacted sites before the industrial period. Since then, you have unimpacted and remote sites that show a steady increase, while the impacted site, they peaked around 1990, 2000, and then they decline. The mercury concentration, they positively correlated with organic matter in an impacted region, and this shows a well-known co-transport of mercury and organic matter to lake sediment. Finally, we're talking about enrichment factor, how much mercury level have been enriched in a specific core. We see a significantly higher enrichment factor in impacted region than in impacted region. And it's highest in Northern Europe, the Tibetan Plateau, and the Arctic, so based on the IPCC region. And it is lowest in South and Southwest South America. Finally, the fluxes of mercury were strongly correlated with aluminium, which again highlights something that is well known, which is the dominant role of sedimentation rates with the mineral. Thank you very much.
Thank you, Svetlana and Adrian. And I know that we only have 12 minutes and we have 3 speakers. So I think we will need to extend 5 minutes or so, but we can still we can only give 3 speakers five minutes. And I don't think that there's a time for oral questions. So if you have any questions, please put in the chat. That would be very helpful for the OESG work. So with this, I think I will hand over to Ronnie, the leader, co-leader of the emission release group.
Thank you, Isaku, and good afternoon, good morning, good evening all. So I'm speaking on behalf of the emissions and releases group. The emissions and releases, so the air, water, and land. Now we have, because you can see from the slide there, we have the EDGAR emissions of mercury, which basically is in tons. The EDGAR has used the IPCC continental region for the period 2010 up to 2020. And we are making use of the EDGAR because it's more comprehensive, combining it with emissions from China, because China has also given us a good deal of information with regards emissions and releases. Now, from the graph there, you can see 2 striking things. There are releases from the West. From the various sectors, we can see that energy or power constitutes between 40 to 60% of their emissions, compared to developing countries, where the majority of the emissions, possibly between 70 to 90%, emanates from the OESG sector. So we can see quite a disparity there between the 2 regions. Next slide, please. Now, with regards even the challenges in estimating the OESG sector, because this graph is basically showing comparison of mercury estimates from the national action plans, and I'm comparing that with the global mercury assessment. But in as much as they closely agree for most of the countries, we can see from this graph that there are some countries which their reporting is quite different from the global mercury assessment. simply because of the assessment in terms of the ASGM. Now, one we can see for Ecuador there, we can see for Democratic Republic of Congo, and we can see for, though the other emissions are small for the other countries, Sierra Leone, Congo, Laos, etc., we can see that there is so much disparity between these countries, and they are and that's reported by the GMA. Now, one thing which we also need to bear in mind with regards the emissions, I forgot to mention it while making the statement on the first slide, is that the emissions reported towards releases on air is far exceed that reported for land and water. So we can see that as addition to the challenges, we have more emissions reporting on air compared to land and water. What we have for land and water, they are mainly localized data. Next slide, please. And so, as we continue to do the emission of releases of air, land, and water, we can see three groups here: air-based emissions, activity-based, and mercury consumption-based. In fact, for Group B and Group C, we have more of the challenges there in terms of the reporting. Again, because the reporting in these areas, the data availability is quite limited. And so most of the reporting for air is much more concise. So when you look at other data sets, the PRTR, the MIA, you realize that you have more reporting with regards to the emissions to air compared to the emissions to land and water. So we still looking at ASGM, which has it still have some underreporting, mainly from the underdeveloped countries, and then we have inadequate reporting for land and water. I think that's all I want to say within my 5 minutes. Thank you.
And thank you, Ronnie, for keeping it with the time. And we thank David Kochman of this Joseph Stefan Institute for working on this release part. So without further ado, I think I will invite Noriyuki Suzuki, who leads the team of integrated analysis. Noriyuki, you have the floor.
Yeah, thank you, Isaku. Status of the integrated analysis work we have done. And we integrated analysis group worked around the 4 type set of key questions. One is the cross-media comparison of observed trends and patterns. Second, the process and source attribution for biota, humans, and other medias. And third one is process understanding and model evaluation. And the fourth one, process source attribution for air and ocean. And we think about all 4 questions. And the summary, comprehensive integrated analysis, we think that is not yet achieved in the current stage of the effectiveness evaluation because of the lack of comprehensive data and scientific methodologies now available for these evaluations. But we have local to regional scientific studies that would be the case studies to imply a potential possible integrated analysis in futures. I listed the contribution, very kind contribution from our members and rosters. We have many good case studies in the list. And we have a strong team with a multi-compartment Mercury modeling and analysis project teams. That model is going to combine atmospheric, ocean, terrestrial, and multimedia mass balance models. You see the reference here. And the team is consisting of the atmospheric model teams, ocean models, and terrestrial and multimedia mass balance models. And looking at available data, we think that left 2 questions, only the case studies can give some implication on that. And the right 2 questions, and third questions, modeling team give some comprehensive, some preliminary answer for the model evaluation, and they give partly the answer, the process and source attribution for air and oceans, but some answer may be coming from the case studies. Next slide, please. And this is examples of the results or the information we used in our considerations. And as I mentioned, on the left two key questions, I think only available information is some case studies that give implication to the future integrated analysis. And these two figures coming from our ROSA expert, Rob Mason and his team. And the figure one shows a spatial distribution of tropical tuna, of mercury in tropical tuna species around the oceans, and also together with atmospheric mercury observation around the areas. And figure 2 shows the variability of the trend of the mercury in the tropical tuna. And I can't say this in detail in this short time, but we don't observe the not very clear trend of that levels in the ocean tuna species of mercury within this from year 2000 to 2010. And I think that this would be the basis or starting point of the future integrated analysis of the effectiveness evaluations. On the left-hand side, modeling team gives some in-depth model evaluation research or studies for this work. And the figure 10 shows the spatial distribution of models trends over 2010 to 2020. And that is showing the plus or minus yearly trends of the mercury levels from modeling and also the observations. And they are working on the model evaluation on how that the different emission scenario we fit it with the representing the better modeling outputs for that meet the observations. And the figure 8 shows the average modeled spatial distribution of mercury in the ocean, surface ocean in the same period. And also that they say that temperature trend can't be linked to the temperature trend of emission in the ocean levels. And our integrated analysis report is something comparing those information to somehow and trying to give not all, but trying to give at least a part of the answers to these 4 set of questions. That's all. Thank you for your attention.
Isaku, your mic is on mute. You are on mute, Isaku.
Sorry. So thank you, Noriyuki. So the last speaker is Ben from China, who's leading the future vision team, which looks into the gaps and challenges. Ben, please.
Hi everyone, I'm Ben from China on behalf of the Future Vision team. Our team task is to respond to the requirements of paragraph 5 and 9 in Annex 2 of COP Decision MC4/11, identifying gaps and the lesson learned from the first round effectiveness evaluation and submitting this along with recommendations to the EEG. We are now compiling the content into a gap and the lesson learned report. Once complete, the parties will be invited to review this report. This report currently consists of 5 main chapters. Chapter 1 and 2 introduce the establishment and work of the Future Vision team, including the coordinates of this establishment, the foundation of the work, the task, the membership, and work timelines, etc. Chapter 3 focuses on the vision. To identify gaps in the lesson learned, we need a reference point. That's a monitor and a data analysis plan that adequately address the scientific questions raised by the effectiveness evaluation while utilizing fewer resources. This section describes such a monitoring and a data analysis approach from 4 perspectives: practicality and sustainability, robustness, and efficiency. It also provides associated evaluated criteria to enable parties or stakeholders to assess and improve the monitoring and the data analysis efforts in the future effectiveness evaluations. Chapter 4 covers the gaps and lesson learned and recommendations. The OESG monitor and data analysis work can be divided into 6 main areas as demonstrated in this meeting. And in this chapter, we identified current and urgent gaps and lessons learned from these 6 areas and provide targeted recommendations. We hope these issues and the suggestions raised here will be reflected in the next round of effectiveness evaluations. The 5th chapter focuses on the comprehensive recommendations rather than addressing specific gaps or lessons learned. This chapter offers comprehensive solutions or mechanism to identify issues, such as establishing regional centers, collecting data in the SGM sector, creating literature databases, mechanisms, and stakeholder engagement strategy, etc. Next slide, please.
So there's a bit of technical problem. Sorry about this.
Yeah, okay.
Yeah, I'm trying to share mine, but it doesn't work. Sorry about this. Yes.
Okay, next slide, please. Okay, I would like to emphasize that the Future Vision team is the most recently established subgroup under the OESG. However, since our formation last October, we have already conducted 2 rounds of the feedback collections for this report. Given that many details regarding gaps and the lesson learned may only become clear as other subgroups near the completion of their work, I am optimistic about finalizing this report by the end of December this year. And finally, I will give 2 common gaps in this report as examples. For more details, please refer to the current version of the report available online. The first common gap is the highly uneven geographic distribution of monitoring data. Globally, the monitoring data from developing countries and the regions are very limited, especially in many countries and regions that host ASGM activities and in critical need of Mercury-related environmental monitoring. To address this, the OESG recommends to providing financial, technical, and personnel support to these countries or regions for conducting monitoring. Additionally, efforts should be made to strengthen long-term monitoring capabilities in these areas, collecting sustained data for better trend analysis. The second common gap is the poor accessibility of current monitoring data. Many important data sets are not effectively shared, and the OESG spends significant resource processing this data in various formats, greatly reducing work efficiency. To solve this, OESG recommends establishing a centralized data hub to uniformly collected, organized, and stored the scattered data, making it easily accessible to OESG when needed in the future. And furthermore, the OESG suggests developing globally standardized data reporting method, which would significantly streamline the data collection process. I hope that these 2 slides have given you a clear impression of the Future Vision team's work. Thank you.
Thank you, Ben. Thank you, all the panelists. And I'm sorry for bad handling of this meeting and we are already 5 minutes over time. So we do not have time for discussion or question comments. So as I wrote in the chat, if you have any question or comments, you can just email me that that would be helpful for the OESG work. The OESG report is the OESG members are really working hard to finalize the draft report as early as possible. So please wait for the good news. And I would like to say a bit of practical words. One is that I think I forgot to mention the contribution of the data depository, which is housed in Biodiversity Research Institute, but also the team leads especially Environment Canada and also Joseph Stephan Institute are working on the really housing the air monitoring and human biomonitoring data. So we are very grateful for that. Also, another announcement is that we are at COP6. There will be the two events, which is called Knowledge Labs. One is about co-organized by the Secretariat and the Joseph Stephan Institute about the modeling team's work. And another is about the human biomonitoring and also data depository by also the Joseph Stephan and the BRI. So if you are on site, please look forward to these events. So with this, I think I will turn to the co-chairs for final word. I think it's Sandy.
Yeah. Thank you very much, Isaku. Thank you so much to all of our media leads for the and the entire OESG scientific group. This has been a really heavy lift for everyone, and to see us at this stage is really quite exciting and something for which we can all be very proud. So I want to thank everyone for attending the meeting today. I think you've seen the tremendous amount of work that's going on and that is continuing to go on. We will hopefully have the draft report sent out to everyone as soon as possible. I'm not making any time commitments because this is a very challenging thing to do, but we will do it as soon as possible. Please know we're working extremely hard on this. And hopefully if you are at the COP meeting, you can attend these knowledge labs. And I won't be at the meeting, but Dom will be there. So if you want to ask any co-chair questions, save them for Dom so he can answer everything for all of us. All right. Enjoy the rest of your day or evening, everyone. And thank you so much for attending. We appreciate it.
Thank you.
Thank you.
Bye.
Thank you. Bye-bye.
Thank you, everyone. Bye for now.
Thank you.
Thank you all. Bye-bye.
Thank you all. Thank you. Thank you.
Bye.
Bye-bye.